All right, so I already have one answer to this question. I'm looking at example 4. This is the bottom of that first page of your handout. We already have one answer, but I just want to use this example to introduce another idea. You could, instead of drawing the rectangles we drew in the last video, which looked like this, and we said, we had a problem, which was that we didn't always have that same top curve and bottom curve. The top curve was always the same, the top boundary of the height of our rectangles, but the bottom boundary changed, which is why we had to split this up into 2 sections to find the area. Watch what happens if I draw my rectangles with a different orientation. I could instead have my rectangles have a horizontal orientation, and in this case the width of the rectangle is a very small change in y, so I'm going to call that dy. And no matter where I draw my rectangles, now with this orientation I have the same curve telling me the leftmost boundary. Every one of those rectangles touches this curve with its left hand side, and I have the same curve, which is y equals x minus 2, telling me about the right-hand boundary of my rectangle. So if I write an integral in terms of y, I'm going to be able to do it with one single integral. Now on the AP test, for a problem like this, they published 2 separate solutions. You could write 2 integrals with respect to x. You could write 1 integral with respect to y. You probably guessed we're going to get the same answer either way. Either method gets full credit. We will find that there are going to be problems in the future where we're only going to be successful if we can write our integral in terms of y. So we're using this problem as sort of a stepping stone. And then you can see here, maybe you didn't know that. So our next job, we're going to do the same example, finding the area of region R using, did I actually say that? I didn't say it in the instructions there, but what we're going to do, we're going to write an integral in terms of y. So come back to this picture and think about this. If I'm going to write an integral in terms of y, I'm going to need to integrate from a to b, but now these are going to be y limits because I'm going to have the height of the rectangle times the width of the rectangle is going to be a small change in y. So now that I've used a variable in my integral, I have to only use that same variable in my integral. So 2 things that I have to fill in. I'm going to have to fill in the limits. I've settled on y as my variable, which means my limits are going to be y values. And in this case, y tells us how high or low we are in the picture. So I'm going to integrate from low to high. So I'm going to need the lowest down. What's the lowest y they got colored in? That's where y equals 0. And the highest y that gets colored in, that's y equals 2. That was shown in the picture. Now I have this problem, which is each of these rectangles is really so skinny that essentially it's a horizontal line segment. So ask yourself, what math would you do to find the length of that horizontal line segment? Well, the y coordinates are the same. You would subtract the x coordinates, and that would be, you want the furthest most right minus the left, so that when you subtracted, you got a positive result. So these are x values. Let's call this x1, y1. If this was x2, also y1, right, because they're on the same horizontal line. What math do I have to do? I have to subtract x2 minus x1. Can I write x2 minus x1 in my integral? I can't because I've already committed to the variable y. So what I have to do is take my equations, y equals square root of x, y equals x minus 2. I'm going to have to rewrite them so that they are solved for x, so that I will have expressions in terms of y, so I can write a subtraction problem inside my integral that only contains the variable y. So this is what we would typically do. We'd say something like y equals the square root of x if I wanted to solve that equation for x, I have to undo what's happening to x. So x is having its square root taken. I'm going to square both sides. I would write y squared equals x. The second equation, y equals x minus 2. I'm trying to isolate x. I have to undo what's happening to x. Well, x is having 2 subtracted, so I would add 2 to both sides, and I would get y plus 2 equals x. So my integral, I've got the limits. That's the lowest y to the highest y, 0 to 2. I need to write an expression for the, in this case, it's more like the length of each rectangle, right? And then multiplied by the width, and I decided the width is going to be a small change in y. So, and we said up here, what I want to do is I want to subtract the right x minus the left x. So the right-hand edge of every rectangle was this y equals x minus 2 curve, but I have to rewrite that in terms of x. So I get y plus 2. Y plus 2. And I'm going to subtract the x-coordinate of the rectangle on the left-hand edge is going to be along this curve, y equals square root of x. But I have to rewrite that to isolate the x, and I get that x equals y squared. So I'm going to subtract y squared. So this is my new integral. It's a one integral answer to the area of that whole region, because when I wrote my integral in terms of y, I had one curve that always gave me the left edge and one curve that always gave me the right edge. All right, so just a quick walkthrough about how to evaluate this integral. This could have been something on your Chapter 6 test. Once you've written this integral, we can evaluate once we have an antiderivative. The antiderivative of y is y squared over 2. Antiderivative of 2 is 2y, minus the antiderivative of y squared is y cubed over 3. So this is my antiderivative. On the AP test, if I was going to guess, I would say that you would probably get 1 point for getting correct limits on that integral, 1 point for putting the correct stuff inside the integral. We call that the integrand. 1 point for getting a correct antiderivative, and 1 point for a final correct answer. It wouldn't be uncommon, especially if you have to write it in terms of y, to get 4 points for a problem like this. Okay, so I'm going to evaluate this antiderivative at y equals 2, and I'm going to subtract what I get when I evaluate it at y equals 0. Remember, when you evaluate at that lower limit, put that whole expression inside parentheses or some kind of grouping symbol to make sure your subtraction gets distributed. So this, whoops. Okay, so this gets partial credit because you've written the correct antiderivative after writing the correct integral, but it doesn't get full credit because you haven't given a numerical expression for the answer. Once you write this is the numerical expression for the correct answer, and in the free response section, that gets full credit. If you make any error while you're doing the rest of this part, you would not get full credit. So you could practice stopping here if your heart can handle that. Some people can't handle leaving expressions unsimplified. So I'm sympathetic to both, but remember on the AP test, do what you got to do. So I have a final answer here, 10/3, which is the same as the answer we got when we had two separate integrals with respect to x. So just to bring it home, if you want to integrate with respect to y, you're going to write an integral that looks like this. You're going to integrate from, oh, that's not the right box. There we go. If you want to integrate with respect to y, you're going to write an integral you want to integrate from bottom to top of right minus left. Notice that if you switch the order of the subtraction, you're going to get the right answers opposite, which you might think would be worth a lot of credit, but then you'd be saying on the AP test that the area of a shaded region is negative, and that's not true. Obviously, the region that we shaded has an area. It got colored in as a positive area. So if this is helpful, this is your shortcut way to think about if I want to integrate with respect to y, the integral from bottom to top of right minus left. But don't forget, you're committed to integrating with respect to y, which means this has to be a dy, which means your right minus left expression has to be also in terms of y. Typically, the functions are given in terms of x, y as a function of x. You'll have to take these equations and solve them to isolate the x to use as an expression in your right minus left inside your integral.